Science 10s. You guys just busted me. I was in the pantry stealing the rest of my kids' Easter candy. Anyway, let's head downstairs and we're going to work on our topic 1 for physics, and we're going to have a look at just some physics review skills for the day. See you down there. Hi Science 10s. Today we're going to work on our physics skills. So just a review of some stuff that we looked already at the beginning of the year, but really important for physics. So welcome to topic 1, physics skills. Alright, so these little guys are going to come back to haunt you, our significant digits. So when we look at significant digits, we need to remember a couple of rules. So the numbers 1 to 9 are always significant, and 0 may or may not be significant. Zeros that are in the middle of a number between 1 and 9 are significant. So these little guys here, they're between numbers between 1 and 9, so those are significant zeros. Then we're going to look at zeros to the left of any number between 1 and 9. So these zeros right here, these are called leading zeros, and leading zeros are not significant. Then zeros to the right of any number between 1 and 9 are considered significant. So these numbers are called trailing zeros, and they are to the right of any number between 1 and 9. So when we're looking at these numbers right here, I know the answers are over here. These would have normally just popped up. But I'm just going to go through these numbers here. So this is a trailing zero, so it does count as significant. So 1, 2, 3 sig digs in this case. Here, 2 more trailing zeros, so 1, 2, 3, 4 sig digs. These 4 zeros here are leading zeros, so they're not significant. This zero here is between a number between 1 and 9. So 1, 2, 3, 4 sig digs in this number here. Again, these are trailing zeros, 1, 2, 3, 4, 5 sig digs. Here, this is scientific notation. This little 4 should have actually been up here. So this is 1, 2, 3 sig digs. We don't worry about our exponent here. We're only worrying about these numbers to the left of the exponent. So that is 3 sig digs there. When we're working on calculations, you never round your answer until the last calculation. When we're adding or subtracting numbers, we're going to take the least number of decimal places. When we're multiplying and dividing numbers, we're going to take the least number of sig digs that were given to us in the question. So if we're looking at 0.0439 plus 0.001, our answer should be to the same precision as the least precise. This one is to 3 decimal places, whereas this one is to 4 decimal places. So our answer should only be to 3 decimal places. So this is a placeholder, this is a placeholder, and this is a placeholder. So 3 decimal places, 0.045 should be our answer. Our 4 here was rounded up to a 5 because the number we're dropping is equal to or greater than 9. So 300 divided by 5, if we look at these numbers here in our question, we have 3 sig digs in this number here, so our answer needs to be to 3 sig digs, so we can just add decimal 0, 1, 2, 3 sig digs in our answer here. Okay. Then we have 300 times 1.432. Again, this is a multiplication question, so our number of sig digs should be the least number of sig digs in our question. That's 3 sig digs in this number here, so 430 is the correct rounded answer. 3,999.5487 minus 52. Notice that 52 has no numbers after the decimal. Because this is because this is an addition or subtraction, then our answer needs to be to the same degree of precision as the least precise. Why did that not erase? There we go. As the least precise. So that is to 0 decimal places, so our answer should have no decimal places. So next we're going to look at formula manipulation. When we're manipulating a formula, we're trying to get one of the units by itself. So when we are trying to isolate the unit, to get it by itself, remember we need to do the opposite, or we need to get rid of the other things by doing the opposite thing. So if we're trying to get rid of something that is being added, we need to subtract it on both sides. If we are trying to get rid of something that's being multiplied, we need to divide it on both sides. If we're trying to get rid of something that is being squared, we need to square root on both sides. And then obviously, if it's being subtracted, add it. If it's being divided, multiply it. And if it's being square rooted, square it. And remember, what you do to one side, you need to do to the other side. We're going to look at these examples next. So you guys can work along with me. Pause when you need to. Hi Science 10s, today we're going to go over just a review of formula manipulation. All the formulas we have today are what we're going to be using in physics. I've got my stuffy class here, so I feel like I'm not talking to myself. So if you see me talking with these guys, it's because I'm going crazy in isolation. Alright, so let's start off with our first formula. Let's do force equals mass times acceleration. So F equals m times a. What we're going to do here, I'm going to ask you guys to solve for a. So we need to get a by itself. A is already on the top, so that's perfect. A is being multiplied by m, so to get rid of that m, we need to divide it by m. So divide by m. What we do to one side, we also need to do to the other side. Because we've got m on the top and on the bottom, we're multiplying it and dividing it. Our m cancels out on this side. We now have a by itself. In proper formula format, we write the unit that we're looking for on the left. So acceleration equals force divided by mass. Perfect. The next one we're going to do is work equals force times distance. This is another formula you guys are going to be working with in physics. So I'm going to ask you guys to solve for force. You guys can pause the video, try this out, and then come back on for the answer. Alright, now that you've paused the video, I know you did, we're going to solve for force. So force is being multiplied by distance. Here we're going to divide by distance to get rid of distance. What we do to one side, we do to the other side. Distance cancels out, and we get force equals work divided by distance. So those first two ones are not too challenging. Alright, the next one that we are going to do is a little bit harder. It's speed or velocity. We'll learn the difference next week. So we're going to do velocity equals distance over time. And I'm going to make this a little bit trickier. I'm going to ask you guys here to solve for time. Now the problem is that time is on the bottom. And if we just divided by d on both sides, we'd have v over d equals 1 over t. And we're not looking for 1 over t, we're looking for t. So just time. So we need to actually move t up to the top. So to do that, we need to multiply by t on both sides. And now we've got t on the top over here. So multiplied by t divided by t on the right-hand side, that t cancels out. And now we've got tv equals d. But we don't want tv, we want to solve just for t. So to do that, we're going to divide by v on this side and divide by v on this side. Our v cancels out. And now we are left with t equals d over v as our final answer there. So that was a little bit trickier. All right, we're going to do potential energy. You guys will learn this near the end of physics. So potential energy is E little p. This is a unit altogether. It means potential energy. It equals mass times gravity times the change in height. So change in height, that's also just one unit. Delta meaning change in. I'm asking you guys to solve for change in height here. So we need to get rid of the m and the g. Just like those very first two that we did, pretty simple. We can just divide by m and g on both sides. So divide by m and g on this side, divide by m and g over here. Mass and gravity cancel out, and we're left with delta H, or the change in height, equals potential energy divided by mass times gravity. Awesome. Good. Okay, the last one is definitely more challenging. You guys did this at the beginning of the year when we started chemistry, and we were doing some of these formulas. And of course we didn't use too many manipulating formulas in chemistry. We maybe used a little bit in biology, but we'll definitely be using a lot more here. So I'm going to give you guys the formula for kinetic energy. So kinetic energy is EK equals 1/2 mv squared. So if you guys remember from the beginning of the year, a better way to solve this is to rewrite this formula to say EK equals mv squared divided by 2. Right? This means the exact same thing as up here, but it's just easier to manipulate. So I'm going to ask you guys to solve for v. So the first thing we need to do is we're going to multiply that 2 on both sides. So here we're dividing by 2, so if we multiply by 2 here, our 2 cancels out. What we do to one side, we also have to do to the other side. So right now we have 2ek equals m over v squared. Let's get rid of that m by dividing it. So divide m on this side and divide m on this side, our m cancels out. So at the moment, let's rewrite our formula just so you guys can see what I'm doing a little bit better. We have 2ek over m equals v squared. Now we don't want v squared, we want v. So what do we need to do? Dinosaur? We need to square root. So we're going to square root on this side. That's going to cancel out the square. And we're going to square root on this side. So when we rewrite this, we've got v equals the square root of 2ek over m. So when we're doing this formula, you guys don't forget at the very end to square root whatever this whole answer is. All right, that's manipulating formulas. Good. Okay, Science 10s, we're going to look at 2 numbers here. We've got a really big number and a really small number, and we're going to change these into significant digits. Again, you guys worked with sig digs at the beginning of the year. This is sig digs, but also having to put stuff into scientific notation. So 1,346 meters, I'm going to ask you guys to change this into 2 sig digs, right? Maybe you only had 2 sig digs in your question. So in this number, our decimal is right here. To turn this into 2 sig digs and into scientific notation, we're going to move our decimal over to the left, and we want only one number to be in front of that decimal place. We're also going to drop every other number except for 2 numbers, and here, this 3 and this 6, we need to look at this 6 here because we're dropping this 6. So what this is going to turn into is 1.4, right? We're dropping the 6, so that 6 tells us what has to happen to this 3. Because it's 5 or greater, we need to round that 3 up to a 4. We moved our decimal place over 3 spots, so we're going to say times 10 to the power of 3, and we're going to put our unit at the end here, meters. So 1.4 times 10 to the 3 meters is this large number, 1,364, put into 2 sig digs. So here's our 2 sig digs right here. All right. Here we've got a very small number, 0.0009876 seconds. We want to change this into sig digs that has 3 sig digs. Here our decimal point is right here. So in this case, we need to move our decimal place over to the right, which means our exponent is going to be negative. So again, we only want one number in front of the decimal place. So 1, 2, 3, 4. Our decimal place moves over 4 spots, and we get 9.8. This is going to be our last number here, so we need to check out this number, only this number here, to see what it does to this number. Because it's 5 or greater, our 7 rounds up to an 8. So we have 9.88 times 10 to the power of negative. Remember, we moved it over 1, 2, 3, 4 spots. So 9.88 times 10 to the negative 4. Don't forget your units in physics. Really, really important. So seconds at the end there. All right, perfect.
All right, I want to go over with you guys now about how to label your graph. So we're going to be doing a lot of graphing in physics. So it's going to be very important that you know these 5 main points that you need to have on every graph, most graphs, for a key. All right, so for sure, all your graphs need to include a title. So that's the T part of talks. Also, all of your graphs need to have your axes labeled. So you can see here, We've got our numbers labeled on our axes, but we've also provided what that axis is telling us about. So it's telling us our height, and we have given it a unit in centimeters. Down here, we've got age in years. So our axes are labeled, which is the A portion of talk. So we always need to have our axes labeled. We'll talk more about the line of best fit, the L here, but you can see that we've drawn a line that is going through basically the middle of our data here. We've got points on either side of it, and we've drawn a line of best fit, which kind of shows us the mean or the average of all of these data points that we've collected here. If we are collecting multiple sort of sets of data, we can provide a key. So that's the K. So say if we were looking at something like the speed of a motorcycle versus the speed of a semi-truck, right? So we would have possibly two different lines here, and we could say, you know, the blue one represents the motorcycle and the green one represents the semi-truck, that sort of idea. And then lastly, we have to think about our scale. So you can see here that this graph takes up all of the possible areas on the y-axis and on the x-axis. So we've not drawn our scale so that we're only taking up, say, this portion of the graph paper here. We're taking up the whole portion of this graph paper. So our graph is nice and big, nice and easy to read. So it's okay if maybe your graph kind of takes up this sort of an area, but I wouldn't want to see anything kind of smaller than that. Try and use as much of the graph area as possible so we have a graph that's nice and easy to read. When we're labeling our axes, here's just a couple of nice hints for you guys to look at. So if you guys just remember the word dry mix, so on our y-axis, we're looking at our dependent or our responding variable, so the thing that is responding to what we are studying. This goes on the y, so the dry portion of this, and then on the x, we're looking at our manipulated or our independent variable, so the thing that we are changing. So for some of your graphs, all right, last thing we're going to look at today is slope. So if we are measuring slope, remember slope is the steepness of a curve. So we can have something that has a really steep slope, or of course, our less steep slopes. When we're measuring, that's hard to say, when we're measuring slope, we're doing rise, so looking at the y-axis, over run, looking at the x-axis. Now your rise is just between the 2 points, so the difference between those 2 points, and your run is the difference between the run of those 2 points. So you're not always doing the entire slope. And that's all for today. Bye.